In the previous video, I've derived these two equations, and these equations are basically the equations that govern what happens in a two-dimensional collision between two round objects. And now I'm going to use these two equations to make a simulation. Equations I've derived in the previous video. I'm going to make the simulation. This tool here, this coding tool I'm using is called processing. I've been using this in my other videos, as you can see in the previous videos. And yeah, it's a really useful tool if you are interested in making visual representations of simulations. And so yeah, I recommend it. I recommend you using it. And yeah, back to coding. So before I start, I'm going to have to define some of the variables I need in this simulation. And first and foremost, we have our masses, and we have two masses, as you can see in the equation. We have m and n, m being the mass of our first object, and n being the mass of our second object. So we have m, and for now I'm just going to give it a random value of something like 10, and n something different like 15. And you realize that I'm using float here for both. Like, even though these are integers, I'm going to use float because float is a decimal value, and we like being as precise as possible. And especially if you're in equations, we're going to have to be dealing with complex calculations involving trigonometry and all that. And so use everything. I'm going to define everything as float variables just in case they appear in some of our equations. And so we have m and m. We're also going to have to define the directions that these balls are traveling in, and they're defined as theta and phi, theta being the direction of m, so our first object, and phi being the direction of our second object, both relative to the vertical axis, and a positive value of between 0 and 360. And what I said just now about the values being between 0 and 360 is going to be really important, because I'm dealing with arctangent and all that, and then I'm going to have to input trigonometric functions into these values that I've calculated using arctangent. And so later on in the video, when I'm dealing with arctangent and cosine, I'm going to explain more about that when I get there. And for now, just remember that all of these angular values are going to have to be between 0 and 360, as in the unit circle. And so we have theta, and for now I'm just going to set it as 0. It doesn't really matter for now. Theta, phi. We also have to define the positions of these two objects. So we have position coordinate. We have x1 and y1, which explains or describes the position of m. So we have x1, again for now 0, y1, then we have x2 for the second object, we have x2 and y2. And we also need our variables for our velocities of these two objects. And we have v, and because we are dealing with two dimensions, we have vx and vy, and also ux and uy. So we have vx first, and vy, we're also going to need ux and uy. And for these values, although they are variables, technically they are variables, but because they need some kind of initial value so that the simulation starts with a movement, if there's no initial movement, we can't do anything. Like, nothing happens. So I'm gonna have to give these four variables some initial value, some random values. It doesn't really matter, unless it's not super fast, then the simulation won't work. So I'm just gonna give them values like -2 here, something like 4, something like 3 here, and 1.5 here. So yeah, it's just random values. Doesn't really matter, unless just remember that they must be given some kind of initial movement such that the simulation works. And now we have we're going to set the size of these two objects, and the size, it's really yeah, size. I'm just gonna see what happens if we vary the sizes of these two balls, like just for fun. So we have, let's say we have R1 and R2, defining the sizes of these two objects. R1 I'm just gonna give a value of something like 30, and R2 something like 40. You know, random numbers, just in case. And another variable I'm gonna need is alpha. So alpha, I'm just gonna say it's ALP. And alpha, if you go back to my previous video, alpha is the angle at which the collision happens. So when a collision happens, there are two circular objects, and alpha is basically the angle that defines the line or the tangent line between these two circles. And so when you draw a tangent line that is tangent, a line that is tangent to both of these circles when they collide, it's going to have, again, an angle between 0 and 360, or let's say 0 and 2 pi, because it's radians. Processing deals with radians. So an angle between 0 and 2 pi from the vertical axis that defines, you know, the angle between these two circles when they collide. And so alpha is going to be 0. For now, it's you know, these are going to be they're variables, so they're going to be given values throughout, you know, when a collision actually happens later on in the coding. And for now, I'm just going to set it like that. We're also going to have du and dv. So dv and du, again, they're variables, so I'm not going to give a value yet. And we have u and v, of course. And we are also going to have a variable for our total energy of the system and total momentum in the x direction, total momentum in the y direction. And yeah, that's basically it for all the variables and constants involved in the simulation. And now let's move on to graphics. So let's define our graphics canvas. It's just a declaration of my canvas. And first of all, I'm going to set up my environment. So the setup part is basically your, you know, setting up the environment of the simulation. So I'm going to have to set up the size. So I've done this quite a lot of times, and I think for this one, like something between 1,000, so 1,000 in terms of length and 700 in terms of height is the most appropriate for this one. I'm gonna have to also set my frame rate as something like, doesn't really matter, 300, quite high, it doesn't really matter. And let's create my graphics. Like this part here, you're if you're used to using processing, it's, you know, default, you just do the same thing over and over again, like for every simulation you make. So this part is not that important. Just set the background as white and you translate to the center. So that's 1,000 and 700, so we have 500 and 350 to go to the center. We also have let's draw my my line. So this here, what I'm drawing now is the boundary of the simulation. So it's going to be a rectangular box, and I'm gonna draw it in blue. So it's 0000FF. That's blue, RGB. We have our line, and now I'm gonna have to go to the one of the corners. So this here is gonna be -500, -350. So that's gonna be the top left corner, because like a minus value in processing is a minus value in the y direction in processing is up, so it's quite different to how you'd imagine it. So that's left, that's up. So this is the top left corner, and to the right top corner, yeah, that's gonna work. And then we have the top right corner to the right bottom corner, and then we have the right bottom corner to the left bottom corner, and then finally we have the left bottom corner to the top left corner. Yes, quite mind-boggling, but yeah, it works. Yeah, okay. And then I just end my drawing. And in the setup, like before I start, I'm gonna have to calculate so these three variables, they're defined because I want to see whether the conservation laws are being obeyed or not. So in theory, these values shouldn't change. But in what could happen is that my equations or my calculations are not perfect, so they might change, or they might change drastically. I don't know. So to test that, I'm gonna print the values for the energy, moment, and momentum, and then I'm gonna see how these values change throughout the simulation. And so we have I'm gonna have to print them. So I'm gonna print ln new line total energy is equal to my total energy, and print ln, which is te total x momentum is equal to tpx here, and same thing for total y momentum plus tpy. And here I'm gonna have to calculate these values. So te, we know that total energy of a system, there's only kinetic energy here, so it's 1.5 or 0.5 times mass times velocity squared. So that's going to be the power of, so v squared is going to be equal to vx squared plus vy squared. So it's going to be vx comma 2, so plus power of vy comma 2, and I'm going to have to add n times ux and uy, because m and v, n and u. Yep, that seems about right. And then I'm going to have to also calculate the values for tpx. So tpx is equal to m times vx plus n times ux. So because it's only in the x direction, it's x momentum. And tpy, same reason, we have vy, m times vy plus n times uy. And so that here is going to calculate for us the initial conditions of the system. Now let's move on to the animation. We have, so this draw function over here, basically it loops over and over again and does the same thing over and over again, and it creates the illusion that it is an animation. And in fact it is an animation. So we have, let's create my canvas once more in the animation, and then set my stroke as 0, translate to the center, and here I'm gonna draw the balls. So this here is, I'm basically drawing my object. So to draw my first object, I'm gonna fill it with green. So my first object is gonna be green. So 0, 0, ff00. I'm gonna make an ellipse. I'm gonna make a circle, but there's no circle function, so I'm gonna use an ellipse function and say, well, its coordinate is going to be x1 times minus y1, because as I said before, in processing, it considers everything in the y direction in the opposite. So when you want to go when you want to go upwards, it's a negative value, and if you want to go downwards, it's a positive value. It's only the y component is opposite, so you're going to have to use minus y1, and then I'm going to have to set the radiuses, or the diameters of the ellipse in both directions. And because this is my first object, I'm going to say it's 2 times r1 because it's diameter. And also the same because I'm making a circle that has equal radiuses, equal diameter in both sides. We have 2 times r1 and 2 times r1, both like that. And this means that, yeah. And also, again, for the second one, we have fill in with, now for the second object, I'm going to use red, so ff0000, and make an ellipse that has a coordinate of x2 times minus y2 times 2 times r2 times 2 times r2. R2 being the radius of my second object. And now I could begin drawing. So canvas.begin draw, and translate it to 500 times 350. Alright, so now what we have, first of all, so there are a few conditions in the simulation. First condition being, if it collides with a wall, its direction changes, and if an object collides with a wall, its velocity changes, of course. And also, if an object collides with another object, its velocity changes. So, firstly, because it's easier, I'm gonna set what happens to the velocities when an object collides with a wall. So we have if x1, so the position of if the position of the first object, if the x position of the first object goes through the right wall, so which is going to be 500 minus r1 because it has a radius of r1. So yeah, you see why I did 500 minus r1, because when the edge of the object touches the wall, its direction has to change. So we have if x1 is bigger, so it goes through the wall, 500 minus r1, we say vx becomes minus vx. So basically its direction in the x component changes. Then we have a similar thing, so it's going to be better if we have an equal sign there. And if x1 goes through the goes through the left wall, so it's smaller than minus 500 plus r1, we also have a problem, so we have vx is equal to minus vx again. So in this case, the velocity of, so vx previously would be negative, so it's going to be heading towards the left, and its direction is now changed to the right. So from a negative value to a positive value here, and here we have from a positive value to a negative value, because the object should be moving to the right direction if it's colliding with the right wall. And then we have if x2 does the same thing. So this here is the same, but the radius is going to be r2. And if x2 collides with the right wall, we have ux is equal to minus ux. And same thing for the left wall, we have is minus 500 is smaller than minus 500 plus r2, we have the same effect. And then we have, that's better. Then we have if, so now we're looking at the y component. We have if y1 goes through the up wall, so we have 350. The boundary of the up wall is 350 from the center. So we have if y1 is larger than 350 minus r1, we're going to say that vy becomes vx minus vy. Yeah. And if y1 again it touches the down wall, so it's smaller than minus 350 plus r1, again we have vy is equal to minus vy. And same thing again, same thing for the second object. So we have if y2 becomes, and r2 and r2, we have uy becomes minus uy becomes minus uy. Yep. And now on to the second condition of the simulation, or I'd say the most important part of the simulation, whereby two objects are colliding. So we have if, and this if statement is going to be quite long. So this if statement here describes the condition for which two balls have collided. And if two balls have collided, how you could imagine it is that the center position of we could describe, or we could define the condition for the collision between two objects by the position of their centers. And so if the two centers of the two objects, their distance must be larger than the addition of the two radiuses, because when it's closer than that, it means a collision has occurred, because we have the center of that and the center of that. If they're touching each other, the distance between the two centers is going to be r1 plus r2. And so if it's smaller or equal to, so if the distance between the 2 points is smaller than r1 plus r2, smaller or equal to r1 plus r2, it means that a collision has occurred. And so if the distance, and the distance is given by the square root of x, distance in the x squared plus the distance the y squared, so power of something plus power of something, and this power here is going to be x1 minus x2 squared, so power of that squared, and that here is going to be y1 minus y2 squared. So if square root of, so that here defining distance is smaller or equal to r1 plus r2, then this means that a collision has occurred. So we could say we could tell this thing to print contact. So I'm going to print contact has occurred, so contact. And then after this contact, as I said before, I want to check whether a collision has occurred or not. No, I'm going to check whether the conservation laws have been met. So I'm going to have to define the total energy once more. The equation for that is here. I've done it before, so I'm going to use the same thing again. So total energy is that, and total momentum in both the x and the y direction are these values. And then I'm going to have to print total, I have to do the same thing once more, so print all of these again. Wait. Yep. And this is just to check whether, my conservation laws are being met or not. So print down total energy, total momentum, and total energy and total momentum. And then, that's it. And now I'm going to have to define my theta and my phi. And this is the important part, because as I said before, all of my angles should be between 0 and 360. That's how I want. And what processing does is kind of a different method to what I want. And what it does is basically it doesn't consider the direction. It only considers which angle it, so for example, if it's a 200, no, if it's a let's say 300 degree, if the angle is 300 degrees, so from the unit, in terms of the unit circle, we have, if that's the center, we have something like that. Although I want it as 300 degrees, what processing would set it as is it's going to be set it to minus 60 degrees, because that is the angle. So yeah, there's many ways to define an angle, but by saying 300 degrees is equal to minus 60 degrees, it could, it's closest to 0 degrees, and so that's why it sets 300 degrees as minus 60 degrees. However, I don't want that, so I'm gonna split the conditions into 4 sections. So we have the first condition is that ux and uy are both positive numbers. So if ux first, vy, it doesn't really matter. Yeah, I'm gonna do vx and vy first. So if vx is positive and vy is positive, this means that the vector v is directed towards the first quadrant, and that's important because I'm dealing with directions here and there again, and so technically 30 degrees and let's say 30 degrees and 210 degrees is different, but what processing does is that they consider 30 degrees the arctangent of something that gives 30 degrees and arctangent of something that gives 210 degrees as the same thing. And I don't want that because that's going to create problems in my simulation. And so I'm going to divide each and everything into quadrants that each vector is directed towards. And so if Vx is positive and Vy is positive, I know it's in the first quadrant, so I'm going to set it as theta is equal to arctangent of Uy minus Ux and not do anything. Because if it's in the first quadrant, the value that processing sets by the arctangent function is going to be the same value as the value that I want. Because in the first quadrant, the angle that processing gives, which is the angle that's closest to 0 degrees, is the same as what I want because it's going to be between 0 and 90 degrees, and there is no way to make it closer to 0, closer to, between 0 and 90 degrees, other than the value that processing gives us. And so here, I don't have to do anything. But next, so I'm going to use else if. So else if v is directed towards the second quadrant, which means that if Vx is negative and Vy is positive, this means that, Vx is negative, Vy is positive, so it's in the second quadrant. Now, if it's in the second quadrant, I'm going to have to add pi. Because, let's say if it's in the second quadrant, so a line that is directed towards the second quadrant, what processing would do is that it will consider it the same as the line that is extended past the origin and towards the fourth quadrant, and this would cause processing to give a negative value between minus 0 degrees and minus 90 degrees, and I don't want that. For example, if it's 120 degrees, processing would give a value of something like minus 60 degrees because it likes giving values that is closest to 0. And I don't want minus 60 degrees, I want 120 degrees, so I'm going to have to add 180 degrees, which is pi in terms of radians. And I'm going to do the same thing for the third quadrant, which is Vx is the third quadrant, Vx is negative and Vy is negative. So if they're both negative, minus 60, 120. So Vx is negative, Vy is positive, yep, and Vx is negative, Vy is negative, yeah. So here now in the third quadrant, if the vector is directed towards the third quadrant, again, there's a problem because something like even though I want something like let's say minus 230 degrees, it's gonna give something like, so a plus 230 degrees is going to give me something like minus 130 degrees. And so if it's minus 130 degrees, to make that into 230 degrees, I'm going to have to wait. If it's minus 230 degrees, if the value I want is minus 230 degrees, it's going to processing would give me a value of 230, 130. So I'd say something like 50 degrees. Yeah, 50. It's going to give me a value of 50 degrees because that's the value that is closest to 0 degrees. And so I don't want that, so I'm going to have to add from 50 plus 180 to get 230 degrees. So again, I'm going to have to add pi, 180 degrees. And then lastly, if Vx is positive and Vy is negative, which means that it is in the final fourth quadrant, this means that I'm going to have to add 2 times pi, so 360 degrees, because for example, if the value I want is 330 degrees, it's going to give me a value something like minus 30 degrees, because that's the value that's closest to 0 degrees. And so I'm going to have to add 360 degrees from minus 30 to minus 30 to get 330. Yeah. So that's how I'm going to define my theta. And just in case that one of these are 0, I'm going to say that else, just say theta is arctan of uy minus u divided by ux. And again, a 0 will not appear. I'm sure about that because, I'm dealing with float values and, 0 doesn't really appear in, complex multiplications of, fractions and all that. Yeah. So, but just in case, I'm just adding this here just in case. And then I'm going to have to do the same thing for phi. So that's done for theta. I'm just going to copy that for phi because phi again is it's one of the angles. It's the angle that defines the second object. So it's just basically change everything to u. So here it's going to be v and v, vy, vx, vy, vx, vy, vx, and vy, vx, and ux, uy, ux, ui. Yep, and then the name of this is going to be not theta but phi, because it's the second object. And then I'm almost done. Here I'm going to set my value for u and v. And we all know that u is equal to ux squared plus uy squared, the square root of ux squared plus uy squared according to Pythagoras' theorem. So we have square root of power of something plus power of something, and that something is ux squared and uy squared. And do the same thing for v. So we have v is equal to vx squared plus vy squared. And then here, now I'm going to have to define alpha. Comment. So here I'm going to define alpha, and I'm going to do the same thing. So I'm going to copy all of that. But now alpha is defined as the arctangent of, alpha, and alpha. So alpha is defined as the arctangent of y1 minus y2 divided by x1 minus x2. And you could check this in my previous video for more information. But basically this is how it's defined in the general case. So here in the first quadrant, this is how it's defined. So if y1 minus y2 is positive, and if both y1 minus y2 and x1 minus x2 is positive, that's the formal definition. But that's not always the case, so I'm going to have to do the same thing I did for everything else. I'm going to set y1 minus y2, x1 minus x2, and set, So if x1 minus x2 is negative and y1 minus y2 is positive, meaning that it's in the second quadrant, for the same reason I add pi. And here, if x1 minus x2 is negative and y1 minus y2 is also negative, so it's in the third quadrant, I'm going to have y1 minus y2 divided by x1 minus x2 plus pi, again, same reason. And finally, if it's in the fourth quadrant, we have y1 minus y2 divided by x1 minus x2 plus 2 pi. And finally, in the case where, you know, things don't work out, just say it is like that. So in the else case, if one of them are 0, it's gonna move on to the else case, and you know, it will work. And then now it's the important part, or the most important part, I guess, which is, you know, defining my du and my dv. So my du and dv, I have the equation that I've, you know, derived in the previous video right next to me. You could check that in the previous video, or you know, back to the start of this video, and we have that du. Yeah, wait. Yeah, so du is equal to, we have 2n divided by m plus n. So yeah, so we have 2 times n divided by m plus n. And we're going to have to multiply that by oh yeah, that's the other way. Yeah, du is 2m times, yeah. So du is going to be 2m times divided by m plus n times u times cosine of phi minus arctan of that, so it's going to be alpha. And then we have plus v times cosine, minus v times cosine of theta minus alpha. Yeah, that's basically it. And moving on to our dv, we have 2 times n divided by m plus n times the same thing, so yeah, we have u times cosine of phi minus alpha minus v times cosine of theta minus alpha. Yeah, that's basically it. And now what we have to do is, first of all, I want to print what my values of du and dv are going to be, because, you know, why not? Du is du, and print, let's print dv first. Yeah, why du first? And then du is equal to du. And then I want vx, my new vx is going to be vx plus dv. Yeah, v is going to be plus dv times cosine of alpha, because, you know, in the diagram of my previous video, you could see that, you know, dv is going to be, and one of them is going to be positive change, one of them is going to be, you know, the changes are going to be in the opposite direction. But because v is my first object, I'm going to set that as positive, so plus dv times cosine again, and vy is vy plus dv times sine of alpha, and then ux is ux minus du times cosine, and uy is uy minus du times sine of alpha. And then what I should do is, I should say x1 gains ux, no, vx, and x2 gains vy, no, x2 gains ux, y1 gains vy, and y2 gains uy every iteration of the code, because that's how the simulation works, by Euler's, you know, method. And then we have n canvas, and basically we're done. So what's this semicolon here? That semicolon hasn't ended yet. Why not? If. Yep, so it should end here, and then the semicolon doesn't have to be here, and then the code goes on. It gains Vx in the x1 gains Vx, x2 gains Ux, y1 gains Vy, y2 gains Uy, and then we end my drawing, end the canvas, and hopefully I'm gonna save this as let's say two balls collide, and if I run it, there's a slight error, so minus. Hopefully it's gonna work. So they don't work. Is there some kind of error in the code? So Vx equals what's going to be the error in my code? Yeah, so after I fix my error, I'm going to come back and see how it works. Mistake. Basically, I didn't set any initial conditions for the position, so the balls started with being collided to each other, being attached to each other, so nothing happened, because the coordinates of both objects were 0, 0 and 0, 0. And so yeah, if I set something, let's say set x2 as 200, then they're going to be separated. And so if I run it now, hopefully, yeah, it works. So you can see that the two balls have different masses and different sizes, and when they collide like that, I'm gonna have to check whether it was elastic or not, but it seems like it is, and you can see that when's the next collision gonna happen? Right about now, like after this, yeah, now, yeah, you can see that it seems pretty good. It seems to be elastic, and yeah, let's see one more. Let's see one more, and yeah, I think that would be the conclusion of my video. So it works, and yeah, I think it works. It's a success. One more, yeah. So that's the conclusion of my video. I'm gonna attach this video file at the end of this video. So yeah, if you'd like it, please subscribe and like this video. And I also I'm also gonna be copying the code text in the descriptions below. So if you want to have a go at making your own simulation, please try that. And again, I think one more is going to happen. No, yeah, okay. Yeah, that's the end of my video. I hope you liked it, and goodbye. Yeah, and as you can see from here, So its total energy is 184.37515. Total x momentum is 25.3. Total y momentum is 45. And as you can see, so the total energy as 184, it doesn't change from the start. And what you could realize is that the momentum values change, but that's because due to the collision between the wall and the object, whereby one of the x components of the or the y components of each object could change change value, so from a plus to a minus. But because you could see that energy is being conserved, we could conclude that elastic collisions are happening, and yeah, energy is being conserved from start to end as 184, and yeah, it's a successful simulation. Thank you.